Conduction and radiation heat transfer. Topics to be covered: basic modes of heat transfer, general conduction equation for one-dimensional and three-dimensional situation, steady state conduction in different geometrics and composite structures for one-dimensional situation, effect of variable thermal conductivity, analysis of heat conduction of system with heat sources and heat transfer from fin surfaces, transient heat conduction in solids with negligible internal resistance and with internal and surface resistance, use of Heisler charts, analytical and numerical solutions of conduction heat transfer problems. Heat transfer. Heat transfer is a study of the exchange of thermal energy through a body or between bodies, which occurs when there is a temperature difference. When two bodies are at different temperatures, thermal energy transfers from the one with higher temperature to the one with the lower temperature. This is the warmer object and this is the cooler object. Heat transfer from warmer object to the cooler object. Basic modes of heat transfer. There are mainly three modes of heat transfer available: conduction, convection, and radiation. Any energy exchange between bodies occurs through one of these modes or a combination of them. There is a combination of convection, conduction, and radiation. First one, conduction heat transfer. In conduction, heat transfer takes place due to temperature difference in a body or between bodies in thermal contact without mixing of mass. The rate of heat transfer through conduction is governed by the Fourier's law of heat conduction, such as Q is equal to minus Ka multiply dt divided by dx, where Q is the heat flow rate by conduction, K is the thermal conductivity of body material, A is the cross-sectional area normal to the direction of heat flow, and dt by dx is the temperature gradient of the selection. There is a picture where conduction occurs. Next one, convection heat transfer. In convection, heat is transferred to a moving fluid at the surface over which it flows by combined molecular diffusion and bulk flow. Convection involves conduction and fluid flow. The rate of convection heat transfer is governed by the Newton's law of cooling. Q is equal to HA multiply Ts minus T infinity, where Ts is the surface temperature, T infinity is the outside temperature, and H is the coefficient of convection heat transfer. So there is a figure of convection where occurs it. See here, this is forced convection and this is natural convection. See the differences. The last one is radiation heat transfer. In radiation, heat is transferred in the form of radiant energy as electromagnetic waves from one body to another body. No medium for radiation to occur. The rate of heat radiation that can be emitted by a surface at a thermodynamic temperature is based on Stephen-Boltzmann law. Q is equal to EAT to the power 4, where E is the surface emissivity, T is the absolute surface temperature, and A is the surface area. There is a picture where radiation occurs. Next topic, thermal conductivity. Recall the Fourier's law of heat conduction, which is Q is equal to minus K multiplied dt divided by dx, where Q is the heat flow rate by conduction, which unit is watt. K is the thermal conductivity of body material, which unit is watt per meter Kelvin. A is the cross-sectional area normal to the direction of heat flow, which unit is m square. And dt divided by dx is the temperature gradient of the section, which unit is K divided by K per Kelvin per meter. There is a picture where T2 greater than T1, material having thermal conductivity K, and this is the area A. There are all these things. K is equal to minus Q divided by A multiply dt divided by dx. dt সমান T2 minus T1, dx equal to d. That means dt divided by dx is equal to T2 minus T1 divided by d. If A is equal to 1 unit, that means 1 meter square, then dt by dx is equal to 1 unit, which is Kelvin per meter, then K is equal to Q. Thermal conductivity of a material can be defined as the rate of heat transfer through a unit thickness of the material per unit area per unit temperature difference. A good thermal conductor has high thermal conductivity, while material with low thermal conductivity is called insulator. Unit of thermal conductivity is watt per meter Kelvin.